Sardinian Ancestry. Sardinian ancestry comes from an island that spent long stretches of history in relative isolation, shaped by harsh environmental pressures and limited outside mixing. Over generations, this created a distinct genetic profile, one where certain traits became far more common than in surrounding regions. Some of the most noticeable effects appear in the blood. Beta thalassemia is relatively frequent, a condition where the body struggles to produce healthy hemoglobin. In severe cases, this leads to chronic anemia and lifelong medical care. Another condition, G6PD deficiency, affects how red blood cells handle stress. Most of the time it stays hidden, but certain foods, illnesses, or medications can trigger sudden breakdown of red blood cells, leading to fatigue, jaundice, and tachycardia. Beyond blood-related traits, Sardinia also stands out for higher than expected rates of autoimmune diseases, like type 1 diabetes and multiple sclerosis. In these conditions, the immune system mistakenly attacks the body's own tissues, either insulin-producing beta cells or the nervous system. The deeper pattern is one of intensity. Sardinian genetics reflect a system shaped under pressure and reinforced by isolation. What once helped populations endure difficult conditions now appears as a clustering of vulnerabilities, reminding us that when evolution narrows its path, its effects can echo for generations. Germanic Ancestry. Germanic ancestry spans much of northern and central Europe, shaped by farming societies, migration, and dense early populations. Over time, certain inherited traits became more common, not because they were perfect, but because they helped people survive in earlier conditions. One key example is factor V Leiden, a genetic change that affects how blood clots. Normally, the body has a balance between forming clots and breaking them down. With this variant, that balance tilts, making clots more likely to form, especially during triggers like long travel, surgery, or hormonal changes. In the past, slightly faster clotting may have helped prevent death from injuries or childbirth. Today, it can increase the risk of dangerous clots. Another trait is iron overload, caused by HFE gene variants. The body absorbs more iron than it needs, and over time, that iron builds up in organs like the liver and heart. What may have once helped during times of poor nutrition now becomes harmful in modern diets where iron is plentiful. There's also a quieter factor. Most people of this ancestry lack the alcohol flush response seen in some other populations. Without that built-in warning system, heavy drinking can feel easier, removing a natural limit. Germanic genetics reflect survival in a harsher past, but when scarcity fades, the systems built for it don't always turn off. Nordic Ancestry. Nordic Ancestry traces to the far north of Europe, regions shaped by long winters, limited sunlight, and extreme seasonal shifts. For much of the year, sunlight is scarce, meaning the body cannot rely on the skin to produce enough vitamin D. Over time, populations adapted not just physically, but immunologically to survive in these conditions. This led to what could be called a winter-tuned immune system, fast, reactive, and efficient against infections in cold, harsh environments. But in today's world, that same sensitivity can turn inward. Autoimmune conditions such as multiple sclerosis and type 1 diabetes appear at higher rates in these populations. In both cases, the immune system mistakenly attacks the body, either the nervous system or cells in the pancreas, like a defense system that can't always tell friend from foe. Light itself becomes another hidden factor. With months of darkness, circadian rhythms can drift, contributing to seasonal affective disorder, a recurring, winter-linked depression tied to disrupted sleep and hormone cycles. At the same time, low sunlight increases reliance on dietary vitamin D, creating a quiet but persistent deficiency risk. Nordic genetics reflect survival in darkness and cold, but when those conditions change, the same finely tuned systems can become overactive, revealing how adaptation can sometimes overshoot its mark. Basque Ancestry. Basque Ancestry traces to a unique population in the mountains between Spain and France, shaped by long periods of cultural and geographic isolation. Over time, this continuity preserved distinct genetic patterns, subtle differences that don't stand out day to day, but can influence certain health risks. One of the most notable traits is a high frequency of Rh negative blood type. On its own, this means nothing, but in pregnancy, it can create a mismatch if the baby is Rh positive. In earlier generations, this sometimes led to serious complications, as a mother's immune system could attack the baby's red blood cells. Today, modern medicine prevents this almost entirely, but the underlying genetic pattern remains. Other effects are quieter. Slightly reduced genetic diversity can make rare inherited conditions more likely to appear within certain families, not because of a specific disease, but because shared ancestry increases the odds of matching variants that negatively affect health. Lactose intolerance is also more common, reflecting a mixed history with dairy consumption. There are even subtle differences in blood clotting tendencies, which can matter under certain conditions like surgery or long travel. Basque genetics tell a story of continuity, but when populations remain stable for centuries, even ordinary traits can slowly concentrate, turning small probabilities into patterns that medicine eventually learns to recognize. Dutch ancestry. Dutch ancestry is often associated with one striking trait: height. The Netherlands is home to some of the tallest people in the world, shaped by a mix of genetics, nutrition, and environment. But height isn't just a visual trait, it changes how the entire body functions. Taller bodies come with longer bones and greater mechanical stress on joints. Over time, this can increase the risk of osteoarthritis, especially in the hips and knees, where more force is placed on cartilage with each step. What looks like strength can quietly become wear. Height also affects circulation. Blood has to travel a longer distance from the heart to the legs and back again. This can raise the risk of blood clots, particularly in the legs, especially during long periods of sitting or inactivity. The same principle extends to the heart itself. Larger body size is linked to a higher chance of atrial fibrillation, an irregular heartbeat that can increase stroke risk. Dutch genetics highlight a simple truth: even beneficial traits come with trade-offs. Height can be an advantage in strength and presence, but inside the body, it asks more from every system that supports it. Italian ancestry. Northern and central Italian ancestry reflects a region of dense cities, long agricultural history, and strong regional genetic patterns. Over time, certain health traits became common enough to shape national awareness, often quietly, without obvious symptoms. One of the most notable is celiac disease, which appears at relatively high rates in Italy. This condition causes the immune system to react to gluten, slowly damaging the small intestine. In many cases, it goes unnoticed for years, showing up only as fatigue, anemia, or mild digestive issues. In Italy, it became common enough to justify large-scale screening, revealing how something once considered rare was actually widespread. Another hidden factor is blood clotting risk. Variants like factor V Leiden and prothrombin mutations can increase the chance of clots, especially during triggers like surgery, pregnancy, or long travel. On their own, they often remain invisible. Cholesterol tells a similar story. Certain inherited forms of high cholesterol can run through families, raising heart disease risk from an early age without clear warning signs. At the same time, some individuals experience lactose intolerance, reflecting regional dietary history. Italian genetics reveal a pattern of quiet accumulation, where conditions don't always appear dramatic, but build slowly beneath the surface, only becoming visible when modern life brings them into focus. Celtic Ancestry. Celtic Ancestry traces to the Atlantic edges of Europe, Ireland, Scotland, Wales, and Brittany, regions shaped by low sunlight, frequent famine, and long periods of relative isolation. These conditions fostered distinctive genetic adaptations, some of which quietly persist as modern vulnerabilities. One of the most striking is hereditary hemochromatosis, driven by HFE mutation. Exceptionally common in Celtic populations, it promotes excessive iron absorption. What may once have protected against iron deficiency during famine now allows iron to accumulate silently for decades, damaging the liver, heart, and pancreas. Cystic fibrosis presents another legacy. Celtic regions have the world's highest carrier rates, likely because carriers once gained resistance to lethal infections, even though children who inherited both mutated copies faced devastating disease before modern treatment. Skin pigmentation reveals a further trade-off. MC1R variants, producing fair skin and red hair, maximized vitamin D synthesis under cloudy skies, but sharply increased susceptibility to skin cancer under stronger sun exposure. Immune genetics add complexity. High frequencies of HLA-DQ2 predispose Celtic populations to celiac disease, an autoimmune response to gluten introduced relatively late into their diet. Even small subgroups, such as Irish travelers, carry severe founder effect disorders like galactosemia. Celtic genetics reflect survival at the margins of Europe, but traits once tuned to scarcity and shadow can become liabilities in abundance and light. Finnish Ancestry. Finnish Ancestry offers one of the clearest examples of how history can quietly reshape genetics. For long periods, Finland's population remained small and relatively isolated. When only a limited number of ancestors contribute to future generations, rare genetic traits can become more common simply by chance. This pattern is known as the Finnish disease heritage. The result is a higher occurrence of certain rare inherited conditions. One example is congenital nephrotic syndrome, a severe kidney disorder that can appear at birth. It affects the body's ability to filter blood properly, leading to serious complications early in life. Another is aspartyl glucosineminuria, a condition that disrupts the body's ability to break down cellular waste, gradually affecting brain function and development. What makes Finland unique is not just individual diseases, but the pattern itself. Multiple rare conditions, almost invisible elsewhere, appear more frequently within this population due to shared ancestry and genetic drift. Finnish genetics tell a quiet story of chance, not adaptation or selection, but the echo of a small beginning where rare traits simply had more room to grow. Slavic Ancestry. Slavic ancestry spans the forests and plains of Eastern Europe, shaped by late expansion, harsh winters, and repeated demographic bottlenecks. Communities often endured famine, epidemics, and long periods of endogamy, allowing chance mutations to quietly persist as populations spread and rebuilt. Some of these mutations carry serious modern consequences. Distinct founder variants in BRCA1 dramatically raise risks of breast and ovarian cancer, not through adaptation, but through genetic drift amplified over centuries. Other inherited risks, like cystic fibrosis and alpha-1 antitrypsin deficiency, reflect mutations that may once have conferred resistance to infectious disease, yet now predispose children to lung and liver damage when both harmful copies are inherited. The immune system reveals another trade-off. Certain HLA patterns, common in Slavic populations, heighten protection against historic pathogens, but also raise susceptibility to autoimmune diseases such as type 1 diabetes and multiple sclerosis, especially in northern climates with limited sunlight. Even behavioral vulnerabilities appear shaped by biology. The absence of alcohol-deterring enzyme variants removes a natural brake on heavy drinking. Slavic genetics reflect endurance in marginal environments. But when survival no longer hinges on plague or cold, the traits that once lingered unnoticed can surface as modern burdens, legacies of resilience that demand new forms of awareness. Iberian Ancestry. Iberian ancestry stretches across Spain and Portugal, shaped by coastal living, regional isolation, and centuries of migration between mainland and islands. This mix created pockets where certain genetic traits became more visible, especially in smaller or more isolated communities. One of the most striking examples is Machado-Joseph disease, a rare neurological disorder found at unusually high rates in parts of Portuguese island populations like the Azores. It develops slowly in adulthood, affecting balance, coordination, and movement as specific brain cells begin to fail over time. Other traits are quieter, but still important. G6PD deficiency appears in parts of Iberia, where red blood cells can break down under certain stresses like illness or medications. Familial hypercholesterolemia is also well studied in this region, a condition that raises cholesterol from a young age, increasing the risk of early heart disease if untreated. There is also a more subtle vulnerability in the liver. Variants in the PNPLA3 gene can make it easier for fat to build up in liver cells, especially when combined with modern diets, alcohol, or metabolic stress. Iberian genetics reflect both movement and isolation, where some traits spread widely, while others stayed concentrated, quietly shaping risk across generations. Alpine Ancestry. Alpine ancestry comes from populations shaped by life in the mountains, cold climates, isolated valleys, and environments where geography quietly influenced health. In these regions, the land itself played a powerful role in shaping biological risk. One of the most important historical challenges was iodine deficiency. Mountain soils often lacked iodine, and without it, the thyroid struggles to produce essential hormones. This led to widespread goiter, an enlarged thyroid, and in severe cases, developmental problems in children. Today, iodized salt has largely solved this issue, but the underlying vulnerability remains. Without careful nutrition, deficiency can return. Altitude adds another layer. At higher elevations, oxygen levels are lower, and the body must constantly adjust. This can disrupt breathing during sleep, causing cycles where breathing speeds up and then briefly stops. Over time, low oxygen can also increase pressure in the lungs, placing strain on the heart. These are not dramatic, visible traits, but quiet physiological pressures shaped by environment. Alpine ancestry shows how geography can leave a lasting imprint, not necessarily through a single gene, but through the conditions people lived in, where even the air, the soil, and the altitude became part of the body's long story. Polish Ancestry. Polish ancestry carries one of the clearest examples of how family history can quietly shape modern health. In Poland, certain inherited BRCA1 mutations became common enough that they are now part of routine cancer screening. These mutations damage the body's ability to repair broken DNA, which raises the lifetime risk of breast and ovarian cancer and can cause disease to appear earlier across generations. Cancer risk in Poland also has an older environmental layer. Stomach cancer has long been influenced by a mix of infection, salted foods, and family exposure patterns. So the danger is not always a single gene. Sometimes it is an inherited setting where biology, diet, and microbes work together over time. Beyond cancer, there is a broader background pressure, heart disease. Like much of Central and Eastern Europe, Poland has carried a heavy burden of high blood pressure, cholesterol, and cardiovascular illness. These risks often stay silent for years, then appear suddenly as heart attack or stroke. Polish genetics reveal a pattern of hidden inheritance. Some risks arrive through specific mutations. Others build slowly through shared family biology and environment, quiet for decades until they are no longer quiet at all. Icelandic Ancestry. Icelandic ancestry comes from a small group of settlers who arrived over 1,000 years ago and remained relatively isolated on a remote island. Over time, this created a population where certain rare genetic traits became easier to trace, and, in some cases, more common. Iceland is often studied because its detailed family records make these patterns unusually visible. One of the clearest examples is a specific BRCA2 mutation linked to higher risks of breast, ovarian, and prostate cancer. Because this mutation traces back to a common ancestor, it appears more frequently in Iceland than in many other populations. The result is not just increased risk, but clear family patterns, where multiple relatives may face similar diagnoses across generations. This visibility extends beyond cancer. Founder effects can make inherited conditions, including some heart and psychiatric risks, easier to detect within family lines. For example, certain variants linked to high cholesterol or mental health conditions appear more clearly in research because of shared ancestry. The underlying theme is amplification. In a small population, rare traits don't stay rare. They become easier to see, track, and sometimes inherit. Icelandic genetics show how isolation can sharpen patterns, turning hidden risks into visible legacies carried through generations. Mediterranean Ancestry. Mediterranean ancestry spans the sunlit coasts of southern Europe, the Levant, and North Africa, regions shaped by early agriculture, dense cities, and centuries of infectious pressure. Life in these environments forged a distinctive genetic landscape, one tuned to malaria, famine, and epidemic disease long before modern medicine arrived. Several hidden disadvantages emerged from these ancient defenses. Traits like beta thalassemia and G6PD deficiency spread because they disrupted malaria's life cycle inside red blood cells. Yet outside that context, they reveal costs: chronic anemia, deadly food allergies, and dangerous medication reactions. Similarly, mutations behind familial Mediterranean fever likely sharpened immune vigilance against historic plagues, but now trigger painful, recurring inflammation that requires lifelong management. Other trade-offs are quieter. Lower lactose tolerance reflects dairy practices centered on fermentation rather than fresh milk. Variants affecting skin pigmentation, while subtle, can increase vulnerability to ultraviolet damage under intense Mediterranean sun. Each reflects adaptation to a precise historical niche. Mediterranean genetics tell a story of survival through adversity, but when threats fade, the protections they shaped remain, sometimes as burdens, echoing battles no longer fought. Baltic Ancestry. Baltic ancestry comes from Northern Europe, where long, dark winters and short daylight hours shape daily life. For months each year, sunlight is limited, and that has real effects on the body, especially when it comes to vitamin production and overall health. One of the most common issues is vitamin D deficiency. Without enough sunlight, the body struggles to produce this essential nutrient, which affects bones, immunity, and even mood. During winter, levels can drop significantly unless diet or supplements make up the difference. At a broader level, the region shows some of the highest heart disease rates in Europe. This isn't caused by a single gene, but by a combination of factors: blood pressure, cholesterol, diet, and long-term stress patterns. High rates of hypertension place constant strain on the heart and blood vessels, increasing the risk of heart attacks and stroke over time. Lifestyle factors can add to this burden. Alcohol use, historically higher in the region, can worsen blood pressure and heart rhythm issues. At the same time, long winter darkness can disrupt sleep and mood, adding another layer of strain. Baltic ancestry reveals how environment and habit can stack together, not through one dramatic trait, but through many small pressures that over time shape the body's overall risk. Balkan Ancestry. Balkan ancestry reflects a crossroads of civilizations shaped by Slavic migrations, Mediterranean influence, and centuries of life in rugged, mountainous terrain. Geography fragmented populations into isolated valleys and villages, where small communities persisted for generations with limited outside mixing. This history left a genetic landscape rich in diversity at the regional level, yet unusually concentrated within local enclaves. Several hidden disadvantages arise from this pattern. Malaria once reached Balkan wetlands, favoring the spread of thalassemia traits and, at lower levels, sickle cell variants. These genes protected carriers, but still carry the risk of severe inherited anemia when combined. Isolation also amplified chance mutations. Founder effects caused rare recessive disorders to become unexpectedly common in specific ethnic or village groups, from metabolic conditions to childhood muscular dystrophies. Endogamy, when two people from the same small community have children, further increased the likelihood that silent mutations would meet. In some rural communities, this raised rates of congenital deafness and developmental disorders. Other vulnerabilities were tightly bound to place itself. Genetic sensitivity to local environmental toxins contributed to Balkan endemic nephropathy, a kidney disease once confined to particular farming regions. Balkan genetics reveal how history can narrow choice. When populations remain small and still, chance leaves a heavier mark, turning geography into destiny and inheritance into an echo of long-forgotten isolation. Romani Ancestry. Romani Ancestry traces back to a migration from South Asia into Europe over 1,000 years ago, followed by the formation of many distinct subgroups. Because some communities remained relatively small or socially isolated, certain genetic traits became more concentrated over time. The key detail is that these patterns vary widely. There is no single Roma genetic profile, but rather many subgroup-specific ones. One clear example is a congenital myasthenic syndrome found in some Romani groups. This condition affects how nerves communicate with muscles. Signals are sent normally, but the muscle response weakens quickly, leading to fatigue, drooping eyelids, and difficulty with movement. With proper diagnosis, some treatments can improve function, but without awareness, it can remain misunderstood. More broadly, founder effects have created clusters of rare inherited disorders within certain Romani subgroups. These are often recessive conditions, meaning they appear when two parents of the same rare gene have a child. In smaller or closely connected communities, this becomes more likely. Alongside this, modern health challenges, like higher rates of metabolic conditions, often reflect environment, access, and lifestyle as much as genetics. Romani genetics tell a story of movement and separation, and in that separation, rare traits can gather, turning quiet variations into patterns that medicine is only beginning to fully map. Eastern Steppe Ancestry. Ukrainian and Eastern Steppe ancestry comes from a region shaped by vast plains, cold winters, and periods of intense social and economic stress. Here, the hidden disadvantages are less about a single gene and more about how environment, lifestyle, and biology combine over time. The most significant pattern is cardiovascular disease. This region has some of the highest rates of heart-related deaths in the world. Conditions like heart attacks and strokes are often driven by long-term factors, especially high blood pressure, which quietly damages blood vessels in the heart over many years before symptoms appear. Another layer is vitamin D deficiency. With long winters and limited sunlight, the body produces less of this essential nutrient, affecting bone health and potentially weakening overall resilience. At the same time, modern lifestyle pressures, diet changes, stress, and reduced activity can increase the risk of metabolic conditions like diabetes. Alcohol also plays a role, not as a genetic trait, but as a strong environmental factor that can amplify existing risks, especially for the heart and liver. Ukrainian ancestry reflects a broader truth. Sometimes the greatest disadvantages are not written in a single gene, but in the steady buildup of small pressures, where biology and environment meet, and health is shaped over a lifetime. Scottish Ancestry. Highland Scottish ancestry comes from one of Europe's most light-limited environments, marked by long winters, heavy cloud cover, and dramatic seasonal shifts in daylight. Over generations, the body adapted to survive in low sunlight, but that adaptation comes with quiet trade-offs in modern life. One of the most persistent is vitamin D deficiency. With limited UV exposure for much of the year, the body cannot produce enough vitamin D through sunlight alone. This creates a reliance on diet or supplements, and without them, bone health, immunity, and overall energy can suffer. Light itself also affects the mind. Long, dark winters can disrupt sleep cycles and hormone rhythms, increasing the risk of seasonal depression. This is more than mood. It reflects how deeply the body depends on light to stay balanced. Other risks build more slowly. Iron overload, linked to common Northern European genes, can quietly damage organs over time if undetected. And without natural biological deterrents to alcohol, environmental habits can more easily shape long-term health outcomes. Scottish Highland genetics reflect life under constant gray skies, but when light becomes scarce, the body must work harder to stay balanced, revealing how even something as simple as sunlight can shape health across generations. If you like this video and want to learn more about different genetic ancestries, check out these other videos.